Okay, so we will continue our discussion about the vortex tube, okay, and the string tube. Okay, and in the previous lecture, I think I gave you the similarity between the string tube and vortex tube. Okay, for example, if this is a string tube, okay, so string tube means this is string line, okay, and then they compose it by the string line is form a tube. And as you know, there is no flow can across the string line, right? 没有任何流体可以穿过流线。Okay, so there is no flow out of from this direction. Okay, so this is the kind of virtual wall, right? 它像个虚拟的墙壁一样。So here is a kind of tube. Okay, so anything can be flow into this A1 area with average velocity V1 bar will be equal to the flow out of from this A2 area with average velocity of V2 bar. A1 V1 bar will be equal to A2 V2 bar due to the continuous equation, okay, mass conservation. So we have the inlet flow here. If you do the integration along the inlet surface 1, A1, and give you the mass flow borrowing flow rate, will be plus, okay, the outlet area A2, and these two area, one is negative, one is a positive. This should be equal to 0. Okay, so that's the continuous equation according to the string tube. And as you can see, if you consider the so-called vortex tube means that this is all the vortex line or vortex filament. Okay, and this is vortex line from this vortex tube. And we have a very similarity between our string line and the string tube and the vortex tube. As you can see, our vorticity, okay, at the inlet area, if you integrate the vorticity along the A1 area, right, plus the A2 area, is also equal to 0 because our flow is what? Our vorticity is divergence free, right? Vorticity is divergence free. Okay, and then since the vorticity is divergence free, right? You can by using the Gauss theorem, vorticity divergence of vorticity equal to 0, and then through the Gauss theorem, you can change from Barrow integral to surface integral. Okay, this is Barrow integral, this is surface integral. So this is omega dot n ds. Okay, should be also equal to 0. So that means anything in that to the surface, okay, along the surface, the whole surface area integration, right, along the enclosed surface should be equal to 0. That means there is no source or sink inside this surface. Okay, otherwise, if you are integrated along all the surface, if there is source or sink or vorticity within this surface, what happens? Your vorticity will increase or decrease. Okay, so here is a kind of the by using the Gauss theorem, okay, from here to here, because this is divergence free, right? This is a vector identity. 它是个向量恒等式 you don't have to prove this is equal to 0. And by through the Gauss theorem, this Barrow integral can change to surface integral. And this give us what? Along a enclosed surface, okay, there's no source or sink or vorticity, okay? And so we have this kind of, okay, if you have vortex tube or there is no flow across there is no vorticity across because this is all vorticity direction. Okay, so only vorticity can enter is this area and this area. So the only two areas has the vorticity go through. Okay, this is A1 and A2. So these two cross sections summation together to the integration should be equal to 0 according to previous this one. Okay. So here we have this equal to 0, okay? And as you can see, if you do the surface integral along the surface, it gives you the borrowing flow rate, Q1 or Q2, right? This is minus Q1 because it is inlet to this surface. This outlet to the surface, we take the outer surface equal to is a positive sign, okay? And the vorticity is the same. Vorticity at this cross section, we have the vorticity integrate with the surface give you what? Give you the vorticity, give you the circulation. Okay, So here is a circulation, and the circulation at this cross section, and circulation at this cross section. So we have what? We have the circulation gamma 1 equals to circulation gamma 2, and gamma 1 equal to A1 omega 1 bar. Bar means the average, okay, average for the whole service, okay, and is equal to gamma 2 equal to A2 omega 2. So you can see the similarity here, okay. Our velocity similar is in the vortex tube is become vorticity. Okay, flow rate A1 V1. This is flow rate. Flow rate become A1 omega 1 is what? Is our circulation. So this is circulation. Flow rate is equivalent to the circulation. So this is string tube. This is a vortex tube. Okay, and this is string line equivalent to the vortex line. Not equivalent, just relatively. Okay, for string line here, this is the vortex line. Okay, so you have this kind of similarity between these two cases. Okay, so here I think I would like to give you the. I think I gave you the Helmholtz theorem of vorticity, part 1. Okay, this is the first part of Helmholtz theorem of vorticity. Okay, so Helmholtz theorem in vorticity give you this. For the circulation at each cross section of vortex tube is the same. Gamma 1 is equal to gamma 2. Any cross section is the same. Okay, this is okay, because this is I think it's true. Okay, you don't have to assume any assumption here. Okay, because our divergence vorticity is a divergence free. Okay, that's always true. Okay. Okay, so according to A1 omega 1 bar is equal to A2 omega 2 bar, right? So you can kind of, if the A1 and A2, the area is changed, our vorticity will change too. Okay, so if you have A1, okay, is larger than A2, it means what? Your omega 2 should be larger than omega 1. Okay, so that means if you have a vortex tube, if they are stretched, becomes smaller cross section, what happens? The vorticity will be increased. Okay, later you will see. Okay, I think I would like to conclude, okay, for this chapter here. Okay, this is kind of, so in this chapter is very short, okay, in chapter 2 is very short. So we introduced what's a vorticity, okay, what's the definition of vorticity. So the vorticity, the physical meaning of vorticity is that is a measurement of rotation of a flow element, right? The flow element, did they rotate, okay? And then, and one thing you have to remember is when you see the vortex, it doesn't mean they have vorticity, okay? Vortex is not equal to vorticity, okay? You have a free vortex and forced vortex, right? And the free vortex, both force, one with vorticity, one without vorticity. Okay, so that's second. I introduce circulation. Right, circulation is a line integral of the tangential velocity component about a closed curve. Right, this is if you along a closed curve and do the tangential velocity component integrate along the closed curve, that's give you the circulation. Okay, and then this through the Stokes theorem, you can change to line integral to area integral. Okay, and this should be curve V here. So curve V give you the vorticity, right? So our circulation is a vorticity to the surface integral. Okay, so this is vorticity integral with a surface give you the circulation of. Okay, so this is Stokes theorem in a mathematically. Okay, so this give you the circulation along a closed curve, C here, okay, is equal to what? Is equal to the total vorticity enclosed, okay, within the enclosed by this closed C, the area integral, okay, because if you enclose a closed curve, there's the enclosed area, and you do the area of that vorticity integral, okay, give you the circulation too. Okay, so that's a kind of, okay, this equation, okay, the physical meaning of this equation. And this one, okay, the vorticity field is divergence free, right? That's the vector identity. 对，它是向量恒等式，你数学上面的。OK， divergence omega is equal to 0. That's always true. You don't have to assume any condition. Okay, in mathematically. So this is divergence omega is equal to 0. That's a divergence free. Okay, it's a vector identity. And by using the Gauss theorem, our boundary integral can be changed to surface integral. So this is a boundary and this is a surface, right? And so this equation is through the Gauss theorem. And this Gauss theorem gives us what? This surface integral equal to 0. That means there is no source or sink or vorticity in the fluid itself. Okay. So inside the fluid there is no source or sink or vorticity inside the fluid because you don't have any assumption at all. Okay, it's valid everywhere. Okay, so inside this classroom we have a flow field, but I enclose a surface area. Okay, inside here we don't have any vorticity can generate inside that area or inside that boundary. Okay, that's it. So where is the vorticity come from? If there is no, if the flow is here, I enclose the area here, right? 我把这个教室圈一个体积出来，这个体积里面没有任何 vorticity can be generated. There is no vorticity can be generated, right? Within this area. And where is the vorticity come from? Still have vorticity, right? 教室里面有没有 vorticity? Yes, right? But where is the vorticity come from? Any enclosed area inside the flow field, they don't have any vorticity source or sink, right? This is a condition we just proved. And where is the vorticity come from? Good question. 没有任何的起始点，也没有任何的 right? Inside the flow field, within the flow field, there's no vorticity source or sink. Is that weird, right? No. Okay. The key word is what? Within the flow field. Okay. 在流场内 Okay. Okay, within the flow field. That's me here. Okay. However, if you have any boundary, okay, boundary. Okay. So the boundary is only possibility is what? Flow over the boundary can be generated vorticity. So vorticity will be generated from the boundary. All the vorticity will be generated from the boundary. Okay. 所以所有的流场的vorticity都从边界层边进来。OK， 在流场中没有任何vorticity可以产生。Remember, we do one of the so-called zero boundary code. Do you remember that? Zero boundary code. 我们有讲了一个叫什么的 zero boundary code， 大家记不记得？ We do the small fluid element, right? We calculate the vorticity for the fluid element under the shear stress, under the stress condition. Okay, they have the stress and they have the vorticity. And we find out the shear stress cannot generate any vorticity on this fluid element. Can you remember that? Where is that? Maybe in the first chapter. more time. Here, right? Okay. Okay, so here is one. Okay, one thing I will recap. Okay, this is fluid element under stress, right? And we try to calculate the torque acting on this fluid element, because if you have a stress and you have force, right? And force acting on this fluid element. Okay, and force acting on the fluid element, we make this torque. This is all the torque, right? This is all the torque. And torque will be equal to what? It will equal to I omega dot, right? When you have a torque, you have a moment inertia times what? Angular acceleration. So this is torque. This is moment inertia. This is what? The angular acceleration, 角加速度, right? So based on this here, you can see the fluid element within the flow field, okay, they should satisfy this condition. And we find out, okay, since this dx, dy, dz is all cancelled, right? And this is dy square and this is dz square. dz and dy is very small value, so e square even smaller. So this is very small, okay, and this one, okay. So when you compare the order of magnitude, okay, we should find out our shear stress, okay, acting on this fluid should be symmetric. You can see this is symmetric, okay, this is symmetric. That means our sigma, this should be supposed to be tau y should be equal to tau zy, okay. So all the stress field should be symmetric, okay, especially the shear stress. Okay, and since the shear stress is symmetric, so symmetry means what? This should be equal. This is equal to 0. That means there is no torque. And there is no torque, they cannot generate any new vorticity, because when you have new vorticity, that means your vorticity will be increased, right? Omega dot is the omega changing, right? Omega change with time. This is omega change with time. So within the flow field, our fluid element, the shear stress acting on fluid element, because the shear stress is symmetric, okay? So we were not able to generate any angular velocity, angular acceleration, right? That's all what? Within the flow field, okay? Within the flow field. OK， 所以在流场里面，我们不会增加任何新的 vorticity， that's the key. OK， and where does the vorticity come from? Where does the vorticity come from? The only vorticity will come from the boundary. OK, so that's the final thing I would like to cover. OK. Most of the pieces they come from the boundary. Okay. 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 Anyway, most of the pieces we generate from boundary. Okay. Okay. So where does the vorticity come from? Okay, because this is divergence free, right? So inside this flow field, there's vorticity. This vorticity it must come from the boundary. So all this, okay, no vorticity can exist, right? On one point in the flow field. Okay, only one point in the flow field there is a vorticity. It's impossible. So there is no source and sink, right? And then so the vortex line, okay, if the vortex line should be form a closed loop. Closed loop, that means this is a closed loop, right? The vortex line should be formed a closed loop. So you can see the vortex ring exists, right? 你可以看到一个漩涡，一个叫 ring， 我们后面会看到 vortex ring， OK， and that exists in the flow field. And then the other one is this vortex line either from the closed loop or they should terminate on the boundary. Okay, 你可以看到 tornado, right? All the tornado is from what? From the boundary. Okay, all the tornado 像龙卷风 one point is one from the boundary. Okay, there's a generate on the surface. Okay, and then spread out, right? But inside the flow field, they don't have any vorticity generation at all. Okay, so all the vorticity generated on the boundary. Okay, that's okay. So that's a very important concept. Okay, for the vorticity. Okay, and we also introduced what's a irrotational flow, right? Irrotational flow, that means all the flow fields without any vorticity. Any point, they don't have any vorticity. So if you are irrotational flow, okay, you have no vorticity upstream and no vorticity downstream. Okay, that's easy to understand. Okay, and finally, Helmholtz theorem of vorticity, part 1. Okay, we have part 2 later. Part 1 gives you the what? The circulation for each closed section of vortex tube should be the same. Okay, so vorticity, okay, so based on this vortex tube, okay, A1 omega 1 should be equal to A2 omega 2. So A1 omega 1 should be equal to A2 omega 2. If they are irrotational in upstream, should be irrotational in downstream because omega is equal to 0. There's no omega 2 because gamma 1 should be equal to gamma 2, right? And then if you have a vorticity upstream, if you have rotational flow, upstream we have omega 1 vorticity, okay? And this vorticity, as you can see, if this is fluid element, okay, and the area is like this, okay, so this is fluid element, and with this area give you the A1 omega 1 for this circulation for this fluid element, okay? And then if this fluid element goes through this contraction here, if I have a flow with a contraction, and contraction means you have a velocity increase, right? There's a partial U, partial X increase. And when you have a partial U, partial X, because a partial U, partial X means you can stretch this, okay? So this fluid element will be stretched, become like this. When you have a fluid element stretched like this, what happens? Our gamma 1 should be equal to gamma 2, okay? Again, because Helmholtz theorem of vorticity part 1, okay? So A1 omega 1 should be equal to A2 omega 2. And here, because this area is A1, and after stretch, the area becomes A2, and A2 becomes smaller than A1 here, okay? So this is smaller area here give you what? Give you higher vorticity, okay? So you can see the relationship, okay? Vorticity is not conserved, okay? 所以说我们的 vorticity 不会说它固定不变，可是它 vorticity 会变，对吧？ And then you may assume, okay, vorticity change from omega 1 to omega 2. That's due to what? It's not due to the torque, okay? Because if you have a vorticity change from omega 1 increase to omega 2, that means you have an angular velocity, angular acceleration. And angular acceleration for that case, for this case is not. Okay, for this case is we just do the pure stretch. When you stretch, okay, it's because gamma 1 should be equal to gamma 2, okay, and gamma 1 equal to A1 omega 1 equal to A2 omega 2. Since our area change, okay, and areas become smaller, our vorticity, our velocity become higher. Okay, that's it. Very similar to like if you are ice skating, right? Ice skating already do that, right? They do the skating, and then when they increase the velocity, they do that, right? Change a small area and spin faster. Very similar, the similarity between this. Okay, area becomes smaller. Okay, our velocity, angular velocity increase, but they didn't have any additional torque to make this rotation. You know what I mean? Because if you do the ice skating, 当你做溜冰的时候, once you do that, you generate torque, right? Once you move that, you generate torque, right? This torque generate, and this torque is what? It's keep constant or dissipate because of friction. You don't have any additional torque, right? 你不会说 做一次，再做一次 ，yeah. You don't do that, right? You don't do the general torque and torque and torque, right? You don't have any additional torque. You just have one torque, but the same one, the same torque, right? And you start to change your shape, and you can increase the angular velocity. Okay. So that's a kind of similarity between here. Okay. Okay, so here is one thing I just want to emphasize. The fluid element is stretched in the emitted flow. And the vorticity is in the stretch direction. This is stretch direction. It's increased. Okay, this is omega 2 in this is stretch direction. Okay, so let's conclude. Okay, our chapter 2 here. Okay. And here there is one more like a note here, okay, because this is not within our textbook, but they are also relate to the circulation. 这边有一些小小的一些额外的 Okay, in the aerodynamics, if you learn the aerodynamics, you will learn the lift. Okay, flow over airfoil, right? Flow. Okay, 流体流过一个机翼 airfoil. Okay, and the lift here will be equal to what? Lift will be equal to rho v gamma. Okay, if this v can be is a 2D flow. Okay, 2D airfoil will be equal to rho u gamma. Okay, I write down here. You can. In aerodynamics, we have this formula. Okay, our lift should be equal to rho v gamma. Okay, gamma is our circulation. V is our friction velocity. Okay, 这就是产生的升力会等于 OK， 流体流过一个机翼产生的升力。And how to prove? You can prove by this. Okay, if this is the flow with a v velocity v here, and we have a 2D airfoil here. Okay, and this 2D airfoil here, we have this span-wise direction is a v. Okay, from here to here is a v. Okay, the distance, and then we have the h here is just our control variant. Okay, so what I did is I do this closed section. Okay, this is this curve. Okay, of airfoil here, and I do this. Okay, I do like a circulation along this path line, along this station line here. So here we have the h is this distance, right? This is distance, and here we have a k, right? The distance from here. So we integrate along this rectangular. Okay, and the circulation you can integrate, right? Circulation you can find out this is circulation. So this is this velocity along this, because we don't have this velocity, because we only have a v velocity is a parallel. Okay, horizontal velocity. We don't have any vertical velocity in the incoming flow. 所以在流场的时候，我们在前面的时候只有 x 方向的速度，没有 y 方向速度，因为它是 free. Okay, so this is 0 times this h, right? So this is this from integrate from here to here, and if you integrate from here to here, what happens? Here our velocity is what? Is equal to v, because we take even near the airfoil, our flow will be increased because of Bernoulli equation, right? But if we take far enough, okay, 如果说我们 integrate this line is far from the airfoil, they will return to the free stream velocity. Okay, so this is from here to here is our v times k. So v times k here is a positive sign here, and from here to here we have a so-called w velocity, because after airfoil we have a downwash. Okay, if you remember this flow called a downwash flow. Okay, w is downwash. Okay, the aerodynamic. Okay, after airfoil we should see some kind of velocity, downward velocity. Okay, so this is downward velocity integrate with this length is what? H. So it's w times h. Okay, so along this orientation, this should be positive sign. And finally this, right? From here to here, because our integrate path is is reverse direction of the v, so it should be take a minus sign here. So minus v times our k here. So vk and vk is a cancel. So our circulation is equal to what? Is equal to WH. Is this downwash times this line here. Okay, that's very easy to understand the circulation. Okay, and this one, okay, how do you calculate lift after this airfoil? 怎么样去估计这个 airfoil 流场流过一个 airfoil 的形状 ？Okay, the lift is in the vertical direction, right? 所以 lift 是在这个方向的。Okay, lift is in this direction. So if you have this direction, that means what? Initially, we don't have a momentum in the y direction. We only have momentum in what? In x direction, right? And when you have a lift in the y direction, what happens? You should generate what? A negative y momentum change, right? Because we don't have any momentum here, but after airfoil, we should see the momentum in y direction, because that will be, okay, that will induce this lift. So how do you calculate the momentum in the y direction after the airfoil? We can calculate what? The incoming flow. Incoming flow, we have a mass flow rate is rho times v times BH. BH is give you the area, right? 这个 B 乘以这个 H give you the area. V times H is give you area. Okay? So rho VA give you what? Give you the mass flow rate. 对不对？所以这个地方我们的 mass flow rate m dot is equal to rho VA and A is equal to what? A is equal to H times V here. Okay, this two. Okay, this is m dot is the incoming mass flow rate, right? And then incoming mass flow rate at the beginning we don't have a y momentum, but after the airfoil we have a y direction momentum. So there is a momentum change in y direction. Okay, and this momentum change in y direction give you the lift. So we can calculate the lift. Okay, so lift is equal to what? Lift equal to m dot. Okay, at the beginning, later we have a w, right? But at the beginning we don't have a w. Okay, so this is outlet condition, inlet condition. Right? After airfoil we have the downwash. Before the airfoil we don't have any downwash. Okay. So that will be equal to rho, this m dot is equal to rho VHV. So rho VHV times W. Okay? So our lift will be equal to rho VHVW. Lift is rho VHVW. That's our lift due to the momentum equation. 可以吗？因为我们有 y 方向 momentum 的改变。Okay, 所以它会增加这个 lift. As you can see, our gamma is we just proved gamma equals to WH, right? WH here equal to gamma. So that gives you the lift is equal to rho VV gamma. Okay, and we can define a cross section lift. 所以这个地方我把它擦掉，你可以看得清楚一点。So here we have the gamma equal to lift equal to rho VV gamma, right? And we can this V is what? V is span-wise direction, right? Span-wise direction. So span-wise, since this is 2D airfoil, so for 2D airfoil, for each cross section here, we should represent as what? As L over V is equal to your lift equal to rho V gamma for each cross section. For each cross section means the unit length of a cross in span-wise direction. OK， 所以你把它除以 b 就是变成单位这个 span-wise direction 方向的什么的 lift。OK， so that's a 2D airfoil. OK， that you can find in the aerodynamic book. OK， so we have the very important formula. Our 2D airfoil lift will be equal to rho v gamma. OK， so circulation will be appear in aerodynamic. OK。所以你可以看到，你学 aerodynamic 的时候，你会注意到 circulation. Okay, and once you know the circulation along this, okay, what? Along this airfoil, you calculate this circulation here, you can estimate the lift. Okay, 所以 sometimes the lift is not easy to measure, okay, especially the unsteady lift. Okay, 有些时候我们在做实验的时候 ，OK， 你要去计算一个鸟的飞行的 lift， 对。Sometimes we like to kind of estimate the lift of the bird, how the bird fly, right? The bird is flying, and I would like to generate the lift, and how large is this lift of a bird, and we are not able to put a load cell on the bird, right? 我们不会把那个鸟的什么装一个力量感测器让鸟去拉 ，impossible, right? So how do you calculate the lift? Usually, just we can measure the flow field. We can measure the flow field of the bird flying, okay, by using some technique like PIV or 3D PIV. Anyway, so once you have a velocity field, you do the closed section integral and calculate the circulation, okay, and then you can estimate the lift, okay. If you see some research in the National Taiwan University, Professor Yang Jingtang. 如果你去看杨敬堂 ，okay, in the National Taiwan University, he do a lot of aerodynamic about how the birds flying, okay, and how do they estimate the lift? They're using that, okay. Okay, so that will be end of story for this chapter here. Okay, I think that will be. We will continue our chapter 3. Okay. Chapter 3 is the topic is talking about the spatial form of Gaussian equation. Okay, so instead of using the Navier-Stokes equation, we still have a sum of the Gaussian equation. Okay, and then here is just kind of discussion about the spatial form of the Gaussian equation, including the Bernoulli equation, including the vortex dynamic equation, all of that. Okay, but later you will see this all generated from the Navier-Stokes equation. Okay, can be derived from the Navier-Stokes equation. Okay, I think we will give you the Kelvin theorem. Okay, again, okay, there's a Kelvin-Helmholtz theorem, but this is part 2 here. I will give you the Bernoulli equation. We will give you the Kolokowski equation and vorticity equation. So this is a topic. Okay, the 4 topic we would like to include into this chapter here. And the Kelvin theorem equation, I think I will just go through this already. This is our previous chapter conclusion, okay? And we just have the Helmholtz theorem for part 1, okay? That's part 1, okay? And here we have a Helmholtz theorem for part 2. And Kelvin and Helmholtz is the same people, but sometimes they call Kelvin-Helmholtz, okay? And this Kelvin theorem can be regarded as a Helmholtz theorem of part 2, okay? So Helmholtz theorem of part 2 is another point of view here, okay? You still consider the invisible flow. Okay, when you see the invisible flow, that means there is no viscosity. Okay, so our Navier-Stokes equation reduced to what? Reduced to so-called Euler equation. Okay, 有没有个我们的 Navier-Stokes equation 会变成什么？一个名词，把那个 viscous term 拿掉，就变成 Euler equation. Okay, this is one thing. Okay, invisible, still under this assumption here, invisible flow. The second assumption here is a conservative body force. We see that before, right? Where do we see that conservative body force? In our homework. Remember our homework? Okay, one of homework 2, I remember, right? We see I asked you to do is what? Give you the Navier-Stokes equation, right? And then I said this is body force is conservative. So I have this, this means the body force is conservative. Okay? And once you have this condition, try to derive, okay, what's the really static, that means that there is no motion at all flow field condition. Okay? I think we should have that here. Okay? Maybe it's the time to discuss. Okay? Let me see. Okay, I think that's the question we have, right? This is the question we have. Okay? So we have the conservative body force. Conservative body force means our body force can be represented as a scalar field, right? This is the 存量场. We take, so this gradient of this scalar field will give you the, okay, this body force field. Okay, so this is body force. It's a vector, and but the vector can be degenerate to the scalar field by the gradient. 所以这个地方我们所谓的 conservative 就是保守立场。当你是一个保守立场，就是你一个向量场可以变成什么？向量场可以变成是一个存量场来讲。那存量场的 gradient 就是这个向量场。Okay, this is conservatively. Okay, and then so here is asks you to do what? To write the necessary relation between rho and phi here. Okay, rho is our density. This is our scalar field, such that the fluid is indeed at rest and no motion at all. Okay, so we have the hint here is to give you ask you to do the momentum equation, right? And let me see, I have an answer here. Okay, answer here. It's not. This is okay. Anyway. So here is our Navier-Stokes momentum equation. That's the Navier-Stokes equation. Okay. So since there is no flow motion at all, so all the velocity will be equal to 0, right? So when you see the velocity, it should be cancelled. Okay. And then so this one velocity, okay, cancel. Okay. There's one velocity. Oh, everything has a velocity inside because we don't have any velocity, no motion at all. 对，这个流场一点动静都没有，连动作都不会流动，对不对？我们讲的是它的 condition. So there is no motion. So our fluid at rest. So U is equal to 0. So only term is not equal to 0 is gradient term here, and the final term is body force term here. So only these two terms. The rest of term is all used with some relate to the velocity. 对不对？所以在这个地方可以看到这 equation 里面 ，okay, all in the Navier-Stokes equation, okay, when the fluid is at rest, U is equal to 0, okay, and that means our Navier-Stokes equation can be reduced to these two terms equal to 0. On the pressure gradient, this is the pressure gradient. This is our body force. Okay, and again, okay. Gradient, pressure gradient, and the body force, right? So one additional condition is what? Additional condition is our body force can be represented as what? Is a conservative. That means they can represent as a gradient phi here. Okay, this gradient phi here. And so our body force, our this is our gradient P here, the pressure gradient, equal to rho times this, okay, the gradient phi here. So we have this relationship, okay, this relationship, this is. And from here, back to our question， 回到我们的问题，我们问题叫你得到的是这个 equation 吗？应该不是，因为我们the equation actually to do is what? Only by using the rho and phi, right? We don't have any pressure because we are in the equation we just write there's a pressure, but we will actually to do is only relationship between rho and phi here. Okay, so P pressure should not appear into this relationship. 对，所有的压力不应该出现在我们的关系式里面，因为我们只要求。So how do we cancel the P here? Okay. So we have the gradient. Finally, we have the gradient here, right? This is so this is the relationship we just write. Gradient P equal to rho gradient phi here. Okay. 这是我们刚刚从 next equation 得到的一个。Okay. So this is if you arrange it, okay, this gradient P mass rho gradient phi should be equal to 0. So one thing to remember later in the chapter 3, we did that a lot, okay? When you have a gradient, you want to cancel this gradient, just do the curve for that gradient. Okay? That's mathematical, okay, technique. Okay? So if when you do want to cancel this gradient, just do the curve of this gradient. Because curve of gradient is equal to 0. You can mathematically, okay? 数学上面就告诉你这样 ，okay? 也是一个恒等式，我们也不用证明。So once you want to cancel this gradient P, do the curve of this equation. Okay? So gradient P is equal to 0. So we have a gradient. So this you do the curve of the rho, okay, gradient phi here, and this give you what? Give you the gradient rho close gradient phi should be equal to 0. That's the condition. Okay? And what's that physical meaning here? 那是物理上面什么？为什么叫做 flow at rest？ 没有任何流动的流场。OK， flow at rest， 所以流体都不动的。OK， 回到上帝创造世界一样，全部都不动的。OK， 就是。Okay, go back to the day one of the God generated the world, right? There's no motion at all. Okay. So for flow motion, flow is at rest. We should satisfy. This condition. Okay. So 这个 close. Okay. 你可以看到 What's this? This is the body force, right? Body force gradient, usually body force will be vertical direction, right? I mean, body force 跟 gravitation 有关。Okay, so this is the gradient phi direction. Usually, right? 一般来讲，重力场就跟这个垂直方向。Okay? Okay, gradient low. 如果说我的 gradient low 在这里的话 ，what happen?我的density field, this low density, right? So gradient low is mean what? I have a variation of density along this direction. 对，我有一个沿着横方向的一个密度变化。When you close this, gradient low close is equal to 0 or not? For this condition, no. Right?对这个物理问题，如果说你的 gradient low 这个方向，你的 gradient phi 这个方向 ，the flow will be flowing, even they don't have any, okay, they will generate the flow motion. 所以你可以看到 in the ocean， 在海里面 ，okay, in the ocean。If I have a gravitation, right, this is body force, always is vertical direction. However, if my density gradient is along the horizontal direction, 怎么 generate density gradient 在 ocean flow 里面 在海流里面，海里面 density gradient mean what? Different concentration of salt, right? 以不同的盐度。OK 啊，我不知道怎么拼。OK, different concentration of OK, because you have a different concentration. Okay, so you will generate this gradient low here. Okay, if once you have just happened here, if you have a gradient low in this direction and gradient phi in vertical direction, generate the flow motion. Okay. 所以这是，如果说你的 gradient low instead of here, we have this gradient phi, and the gradient low is this. What happened? There is no motion. 对啊，如果说我 gradient low 是这个方向的，垂直方向就没什么。Once you have an angle, you generate motion, right? So depend on your the density field, 你决定你流场会不会完全静止，还不会完全静止。Okay, and here is also this term will be equal to actually is a vorticity. This will be generated vorticity. So usually I just kind of want to emphasize when I say there's no vorticity can be generated within the flow field. That means I didn't count body force gradient or the density gradient at all. Once you have density gradient, okay, the vorticity can be generated inside the flow field. Okay, under this condition, I'm sorry. Okay, under this, you will generate the motion and generate the vorticity. So here, okay, I will stop here. Okay, so this is a true condition. Okay, for you. Okay, and the flow motion will be at rest. Okay, so 如果流体完全不动的话，我们要符合这个条件。Okay, so let's take a